Welcome back. I'm extremely satisfied as the next speaker is here with us offline. So, at least I have some kind of offline interaction today, and it really, makes me happy. And please welcome our next speaker, Konstiantyn Bokhan, who is, a lead software engineer in N-iX company. And he's going to share with you the topic CD4ML based on Azure and Kubeflow. I hope it will be very interesting for you, as I hardly know what it means, but, I will be looking forward to the presentation and listening very carefully with you. So a few more words about Konstiantyn, who is a technical lead in N-iX, as I mentioned. He focuses on data science project. He leads data science project in several areas, computer vision, NLP, and signal processing, as well as consults clients regarding digital transformation with AI. Konstiantyn, I'm so pleased to welcome you here in our studio. And at least now we know that we will not face any technical issues as we had, with the previous presentation. So how are you today?
Fine, thank you. I'm happy to see that Lviv becomes more beautiful every my visit.
Great, yes, thank you for this. And you are lucky with the weather. It's not happening. It doesn't happen so often. So Konstiantyn, please, the floor is yours, and we are looking forward to your presentation.
Thank you. Hello everyone. My name is Kostiantyn Bokhan. I'm technical lead at N-iX. And here at N-iX, I'm focusing on data science projects. Additionally to hands-on data science and software development, I consult our clients on digital transformation with artificial intelligence. So, the topic of my daily speech has been inspired by my clients who came us with questions about how to bring their AI products to production. Considering this, I'm going to talk about continuous delivery for machine learning. Because my client native project is based on Azure, and we implement continuous using Kubeflow. So I'm going to share my experience with also. Next slide, please. Today I'm going to touch the next topics: introduction to CD4ML, Kubeflow, use case of Kubeflow, and installing Kubeflow on Azure. I will provide some tips and tricks. Next slide, please. I have to deal with the automation of machine learning routines for more than 5 years. On this slide, you can see a screenshot from my speech at EU Ukraine 2016, where I presented a custom automation framework that had been implemented at Samsung R&D Ukraine. Where is continuous delivery for machine learning? A quite comprehensive description is provided in Martin Fowler's blog in the article Continuous Delivery for Machine Learning. Let's look at the definition. The next. So, the previous, please. Continuous delivery for machine learning is a software engineering approach in which a cross-functional team provides machine learning. And I would like to stop here because from my side, cross-functional team is a key point. Today, business owners and managers usually build a data science team if they need a product that uses artificial intelligence, and if they are lucky enough, such a team will produce a great POC or even MVP and got stuck there. Definitely, data science are very good at math, data science, neural networks, and so on and so forth. But it's not enough to release a product to production. So obviously, the experts with different skill sets and knowledge areas should work together in collaborative way to release a great product. The second thing, the key thing, is automation. As much as possible, it can assure that the process of releasing AI-based products is reliable and reproducible, and we can release at any time. The next person. There is another term, MLOps. Let's look at how it's defined in the Google documentation. MLOps, continuous delivery and automation pipelines in machine learning. As you can see, it's very similar to continuous delivery for machine learning. But MLOps is an ML engineering culture and practice that aims of unifying ML system development and ML system operations. Considering this sentence, it's very close to the definition of classical DevOps. To understand how to differentiate DevOps from MLOps, let's look at software development life cycle. Traditional DevOps is aimed at automation and orchestration traditional software development life cycle. But the next, artificial intelligence-based products have additional parallel cycles, model development life cycles, and dataset life cycles. And obviously, MLOps is aimed at automation and orchestration of these additional life cycles. Similar to differentiation between DevOps and MLOps, continuous delivery for machine learning contrasts to traditional continuous delivery, considers those additional life cycles, model and data. On this schema, you can see a mapping traditional data science pipeline stages to different axes, code, model, and data. For each dimensional, appropriate infrastructure should be built. For example, for code, Git, continuous integration, continuous delivery, test environments, and so on and so forth. For models also, we need to create storages to create kind of high-performance computing for running training tasks. We need to develop and deploy model management systems. For data, also storages and data management systems. All of these tasks should be automated, of course. So as you can see, continuous delivery for machine learning is a significantly more complicated problem. Let's consider the data preparation stage. This stage is aimed at preparing data sets, training, validation, test sets. For this, we might need a labeling or a markup tool, data cleansing, and data validation tools. So at least continuous integration and continuous delivery for these tools should be created. Additionally, we can implement raw data pre-processing automation or even semi-automated data labeling. It will speed up the data preparation stage. Please consider without a data set, model building can be started. Continuous integration and continuous delivery for markup tool can be implemented here, as well as some automation of data pre-processing. At the model building stage, training code and training data are consumed, and we can implement different level of automatization here. Continuous integration, continuous delivery for training code. We can implement and deploy Jupyter Notebook service for data science experimentation. We can automate pre-processing, augmentation, model training, and also we can start using AutoML here. The evaluation code is used to evaluate the quality of candidates' models at the model evaluation stage. The output of the model evaluation stage includes a chosen model with the best performance metrics, and at the data dimension, model parameters and performance metrics of all evaluated models are produced. And we need to track and store such data for further analytics, because we can return to this data analyze to find the best models that perform the best, and can compare different models based on different technologies between each other. For example, to discard bad hypotheses and improve utilization of computational resources. Traditional, the experimentation stage that includes model building as well as model evaluation stages is the most time-consuming and unpredictable stage of AI product development. So automatization can significantly improve this by speeding up experiment cycles, when many hypotheses can be checked in parallel, as well as model quality can be improved continuously with improving, for example, quality of data sets. Because usually when we start a data science project, we don't have enough samples in our data sets, and we may collect more samples during the project development. Improvement in iterations considering continuous machine learning, continuous improving our models can be run automatically as soon as data sets is updated. At the model productionized stage, the chosen model that prepared in the previous stage can be integrated with our application. It can include different format on conversation, for example, hatering TensorFlow, saved models for serving. Obviously, such tasks should be also automated. Let's look at testing stage. We are talking about testing artificial intelligence applications, and we should differentiate model testing and application test, because model tests show how perform models by itself. And at the same time, application level tests, additionally to model integration test and sanity check and smoke checks, show how performs the application in terms of business metrics. I will return to Kay question a little later. Automation at testing stage is a common practice today. At the deployment stage, models and applications should be delivered to a target environment. There are several options. Delivering model and application separately, for example, when we use serving service like Seldon or KF serving or TensorFlow serving. In this case, the application requests inferences through serving REST API. The second point, delivering models and application also separately, but applications download and update models on their own through REST APIs, for example. And the third option, when we deliver an application model together in a Docker container or as application installation package, for example, an APK. The monitoring and observability stage is aimed at health checking, collecting usage statistics, detecting anomaly stages, and tracking business KPIs. Such data will help us to find weak points of our models, detect use cases that have never been covered in our data sets, and so on and so forth. Please, next slide. Let's look at QA a little deeper. In this slide, you can see a classical test pyramid extended some additional components. Clearly, the quality of application is not only based on the quality of applications code, but also on the quality of data sets and models. How many unit tests have been written for data preprocessing by your data scientist? So You can see the test permit for AI project includes elements related to additional life cycles, data, and models. As a side effect, the test permit for AI project reflects the increasing complexity of artificial intelligence projects. If we are going to create a high-quality AI-based product, we should write unit tests for model building pipelines, dataset pre-processing models, as well as additional performance degradation tests for models, for example, to check resistance to adversarial attacks in case of safety-critical systems. I would like to note there are some terms which definitely are very close to continuous delivery for machine learning. It can make confusing. For example, continuous machine learning. I used to use this term in my previous presentation at IE Ukraine 2016, and there is an open source library for implementing continuous integration and delivery in machine learning projects. So I think we can consider this term as a synonym or subset of continuous delivery for machine learning. The next, incremental or continual machine learning, is a method of machine learning in which input data is continuously used to extend existing model knowledge to further train the models. So this method can be used as part of continuous delivery for machine learning. The wiki definition of AutoML is very close to continuous delivery for machine learning also. Is the process of automating the process of applying machine learning to real-world problems. AutoML covers the complete pipeline from the raw dataset to deployable machine learning models. At the same time, as real AutoML tools are focused on automation, only data science things. Feature engineering, feature extraction, feature encoding, data preprocessing, neural network architecture research, and so on and so forth. So AutoML can be also used as a part of continuous delivery for machine learning, especially at model building and evaluation stage. There are a lot of tools that can be used for creating continuous delivery for machine learning. Some of them provided by cloud providers, for example, SageMaker from Amazon or Azure Machine Learning. Among standalone tools, it's worth to denote the next: PyCharm, MLflow, and of course, Kubeflow. We have decided to use Kubeflow due to it's based on the cloud-native architecture as our project, and it allows us to unify technology stack. Wiki says that Kubeflow is a free and open-source machine learning platform designed to enable using machine learning pipelines to orchestrate complicated workflows running on Kubernetes. But continuous delivery for machine learning can be implemented as combination of machine learning automation tools and classical DevOps automation tools. Let's consider models that Kubeflow includes. For example, very famous and most popular tool for data science experiments, the Jupyter Notebook service. It allows creating other Kubeflow components right from a notebook, for example, pipelines, or even model serving. Kubeflow pipelines is the core of the Kubeflow that provides automation of machine learning workflows. Katip is a tool for tuning hyperparameters and AutoML. And very useful tool, metadata, for tracking metadata, including versioning of models and data sets. Sets of tools for model serving. KF serving, Seldon, TensorFlow serving, NVIDIA TensorFlow inference server, and so on and so forth. As well as different Kubernetes objects for distributed trainings. For example, TensorFlow job, PyTorch job, and others. A quite comprehensive list of components is presented in this picture from Kubeflow documentation. The next slide, please. The next. So as you can see, Kubeflow is a very complex set of tools, and it can be deployed under Kubernetes and provide very useful components to deal with data science automation. Our recent project where we try to implement continuous delivery for machine learning is kind of worldwide logistic platform. This platform operates many types of data, documents, events, sensor data, pictures, and video from cameras, mobile and stationary cameras. We work on AI components that automate and robotize numerous business processes. Such components include microservices, mobile, and embedded applications. As you can see in this slide, our project includes a lot of technology components. We release a lot, work on a lot of different data science components that include computer vision components, object detection, object classification, segmentation. Also, we work on NLP, fuzzy document matching, and language modeling, template matching. Also, we developed some components related to signal processing, especially from IoT devices, pattern recognition, and so on and so forth. So let's look at how we optimize the development process with Kubeflow. We set the next goals. We use Jupyter notebook services that can be scalable. Any number of simultaneously running netbooks on GPU or CPU. We implement automatization of all stages of deep machine learning development in scale for processing, dataset preparation, as well semi-automation labeling, augmentation also. Model training and verification. We have tried to leverage AutoML also and optimize of model hyperparameters. The very important goal is to track and analyze the result obtained after model training. This metadata includes model versioning and other metadata like training configuration. And we implement model as a service using kind of tools of model serving, like TensorFlow serving. Let's look at how we implement computer vision experiments. Computer vision engineer creates a Jupyter notebook session on Kubeflow. In the created notebook, computer vision engineer can import any packages, any required packages from a Git repository with, for example, Git tool, or from Azure Artifact repository with pip tool. When computer vision engineer runs different parts of the Jupyter notebook, the Kali tool translates source code from the Jupyter notebook into Kubeflow pipeline and runs it in on Kubernetes cluster in Docker pod. The cloud source can be called from the Jupyter notebook directory. It's very useful when we need to test integration are serving with other microservices from our very big system. When you bundle Jupyter notebook in Kubeflow, you can use the firing library to submit training jobs using TensorFlow jobs or other tools like PyTorch job. Data sets are available on Azure Blob Storage, and we can connect any Azure Blob Storage to the pod that runs Jupyter notebook. The training job can run single node or distributed on the same Kubernetes cluster, but not inside the notebook pod itself. So the very useful thing of Jupyter notebook session on Kubeflow is possibility to run distributed trainings on Kubernetes cluster. So in the next slide, you can see how we build models, train models, and validate models pipelines. For example, a developer make changes in pre-processing module, or for example, release new neural network, or for example, starts a hyperparameters tuning strategy, etc., etc. Azure pipeline receives a webhook and triggers our Azure pipeline that starts AutoML pipelines that builds model, validate models, tune our hyperparameters of our neural networks. Such AutoML pipelines can be triggered by dataset changes as well. The very useful thing that AutoML pipelines can be run in parallel, and we can check many hypotheses in the same time. So it allows us to speed up experimentation stage significantly. The result of training pipelines are shown on the dashboard provided by Kubeflow. Let's look at how we deliver embedded application. In this case, a developer makes change in our embedded software, creates, for example, a pull request. Azure pipeline service detects changes and trigger build pipeline, integration test, and performance test. If build and test are successful, we update Docker image with embedded software service, and we integrate recent neural network models and release our embedded software to embedded devices, where as a Docker image that consists of software as well as models. The next use case, continuous delivery for mobile applications. The first steps are the same, but different stages for, we implement different stages for delivering applications and our models. And we consider several ways. One of them is to deliver models and applications separately, when application can download recent neural network directly from Azure Blob Storage. Or we have some cases when we have to upload our models to Firebase storages, and then our mobile application use a Firebase API to serve embedded models directly on devices. The next use case show how we evaluate and track the quality metrics of mobile applications that consist of recognition pipeline. This use case helps us to detect if new changes of source code or data set or model don't worsen quality metrics. We implement an evaluation Kubeflow pipeline for this. It can be triggered from Azure pipeline, manually by a developer, or from model building pipeline. The old model will be replaced in the mobile application. The very interesting thing that I would like to denote that this pipeline creates an Android emulator. For this, we have to configure special Kubernetes nodes that support nested virtualization. The pipeline consists of 3 stages: creating an Android emulator, pushing the model application to the emulator, and running evaluation Android instrumentation test, extracting result and calculate metrics. The next slide, please. On this slide, you can see a screenshot of this pipeline on Kubeflow. The next use case demonstrates how we collect usage statistic and related data and use it to track performance in production, find pitfalls of our model applications, as well as collect samples for our datasets. Our mobile applications include a debugging mode when the applications collect different data, including pictures, recognition results, timings, and some user interactions. This data periodically is updated to an Azure Blob Storage. When a new set of samples arrives, the Azure Blob Storage configured to generate an event. And we have special microservice that catches these events and triggers our pipelines. Also, this microservice provides paths where the new data can be taken. Metrics that estimated by this pipeline are exposed to Grafana dashboard, and our clients using this Grafana dashboard with application metrics can track how perform our application and models in production. Let's look at the use case that shows how we validate labeling quality using Kubeflow pipeline. We have developed a pipeline for labeling samples and generating special templates for template matching task that is executed on our mobile devices. The success of template matching depends significantly on labeling quality. The template generation includes its own validation metrics, but we have decided to use the mobile validation pipeline for double checking, because template pipeline metrics calculates only metrics based on labeling pipelines, source code. They use it for labeling our templates. But in case of our mobile application, we need to assure that mobile application can successfully match new templates. And for this, for such double checking, we implemented this pipeline. This pipeline is similar to one from the previous use case, and also it's triggered by the template generation pipeline. The model application is run in Android emulator and downloads updated templates, then tries to match the new template using test set provided for this task. If success, the new template is accepted and user notified about this. If not, user has to relabel the template. In the next part of my speech, I would like to share some tips and tricks regarding installing Kubeflow on Azure Kubernetes service. There are several issues that makes the installation process not obvious. For example, Istio is outdated. Istio CTA, very useful tool to manage Istio, is not supported. Knative part is outdated. Embedded Knative is not supported. Uninstall of the recent Kubeflow can fail. So, considering all these issues, I've done several experiments and create a workflow that allows us to deploy a very stable Kubeflow environment. Let's look at the installation workflow that has been formed as a result of my experiments. The workflow consists of next stages. Creating Azure Kubernetes service, creating and linking Azure Kubernetes container registry, installing Istio, deploying Knative, installing Kubeflow, deploying KF serving, and deploying other components. Let's start with creating Kubernetes cluster. And installing Kubernetes cluster should be started from resource planning. For instance, Kubernetes cluster for data science tasks should include nodes with GPU. But for example, if we need run Android emulators, we should consider nodes that support nested virtualization. Or for example, we need special distributor storages, and for this we need to consider additional nodes that are optimized for distributor storage systems. Please consider that recent version of Kubeflow has never fully tested on Kubernetes cluster with version greater than 1.16. So, in this slide, you can see a command that creates Azure Kubernetes cluster, and very important things, several options. For example, node pool name. This node pool name can be used further to select where our services, where our pipeline should be run. Because, for example, data science pipelines that require GPU resources should be run on nodes that have GPU resources. But for example, system Kubeflow system components should be run on nodes that have only CPU resources in order to avoid deploying these components to nodes with GPUs, because in this case such components will take some resources that can be required for data science pipelines. In this slide you can see how we can select where a pipeline should be deployed. We can use node selector agent pool and put here node pool name. The next step, we can start, for example, we can start creating Azure Kubernetes cluster with common node pool set. But if we are going to run data science pipelines on this Kubernetes cluster, we can add additional node pools that consist of nodes with GPU resources. In this slide, you can see the command that adds additional node pool with GPU resources. Also, we can use node selector again pool with name of this node pool to select this node pool during deploying our data science pipelines. The next slide, please. The next step is creating an Azure container registry and linking with the AKS, with the Kubernetes cluster. It will be a bit hard because, unfortunately, linking with Kubernetes cluster require some additional roles in Azure, and it's very high roles, and we usually don't have such very high role to link our Azure container registry with Kubernetes cluster. But we can use we can link container registry with Azure Kubernetes cluster using token linking. For this, we need to generate tokens, and then we can create the secret that contains tokens parameters, I mean username and password. And then we need to patch default service account. After this, we can our Azure container registry will be linked with our Kubernetes cluster. The next slide, please. The next stage is installation of Istio. It's pretty easy because Istio project provides very useful tool, Istio CTL. And what we should consider is requirements for Istio that provided by Knative, because the next step is to install Knative components, and Istio configuration should provide special sync, especially for Knative. In this slide, you can see these parameters. For example, we should disable proxy auto-inject, and also we can select node pool, especially CPU-based node pools, where Istio components should be run. What's the next? The next step, installing Knative. As I said, the recent version Kubeflow includes only outdated version Knative, and running commands presented in this slide, we can install the recent version of Knative. The next one. And at the end, we can install Kubeflow. As you remember, I said that the recent version Kubeflow consists of updated components, and such component we install separately. So we need to disable these components in Kubeflow configuration in kfctl istio file. In this slide, you can see what we should delete from the Kubeflow configuration. Such blocks of configuration should be deleted for all components that are installed separately. After that, we can run the kfctl tool to install Kubeflow. For deleting Kubeflow, we use the same tools, but with command delete. The next slide. After installing Kubeflow, we should check if Kubeflow runs. So in this slide, you can see command how to check if Kubeflow has been deployed successfully on Azure. The next slide. And at the end, I would like to share my experience to serve TensorFlow models. As I said previously, the recent version of Kubeflow consists of outdated kf serving component, and this component can't serve TensorFlow engine version 2. So it's why we have to deploy all these components separately. And in this slide, you can see configuration of TensorFlow TensorFlow serving task. As you can see, storage URI parameter consists of URL to our TensorFlow model. Here it is MNIST. And at the end of this slide, you can see command that deploys kf serving component to Kubeflow. After that, we can request inference directly using REST API, using TensorFlow REST API for saved models for TensorFlow serving. The next slide. KF serving can be installed also very easily, but we should consider that namespaces should be labeled to allow us to deploy KF serving components to these Kubernetes namespaces. In these slides, you can see commands that provide such labels for our namespaces. The next one. In this slide, I provide example of requesting our TensorFlow serving model, especially for metadata, and you can see result of such request. Thank you. It's all from my side. Any questions?
Konstantin, thank you so much. You were very generous sharing your deep experience using Azure and Kubeflow. And for the moment, I don't see the questions in the chat. So people, if you have any, please, you still have a few minutes to ask them. So in the meantime, I will ask, my question. So could you please explain me, the person maybe, not maybe me, I'm not so deeply involved with this technology, but to other participants, the benefits of using Microsoft Azure in comparison to other cloud providers? Like
I'm not sure that there is kind of preference, because Azure, it's requirements of our client.
Ah, okay. Okay, so, but thank you. And could you also then please share with us some challenges of CD4ML?
Challenges, as I said, we need to implement much more continuous integration and continuous delivery stuff comparing to classical continuous delivery. So, because projects that is based on artificial intelligence requires much more testing, much more automatization. So, such projects are very complicated.
Okay, thank you. So, and then, there is one more question here by my side. Are there any alternatives to Kubeflow, and what are some distinct features of Kubeflow?
Yes, for example, MLflow, PyChartDerm, or if you want to deploy continuous delivery for machine learning by yourself, you can use services provided by Kubeflow, by cloud providers, for example, Amazon SageMaker or Azure Machine Learning, and most of these features are available in cloud version of continuous delivery for machine learning technologies.
Thank you. And then, maybe, the last but not least question I would like to ask you. What's your favorite algorithm that you can explain to me in a minute?
My favorite algorithm? I don't know, maybe my recent algorithm that I have just implemented in our mobile application. It's kind of edit distance.
Oh, okay.
Yes, we use edit distance for document and template, for document matching, for fuzzy document matching in our project.
Oh, that's very interesting. Thank you, Konstiantyn. Just give me a few seconds to check our chat in the IT Arena application, but I still don't see any questions. If you have any, please, I'm sure Konstiantyn will be happy to answer them via email or somehow. And thank you. So thank you again for being with us, for coming to Lviv, for being with us offline.
Thank you for providing such beautiful stage.
Yes, I agree with you.